Some colonies enter spring and are nearly unmanageable within 6 weeks. Others, started from similar stock in similar yards, never quite recover from winter. The difference is rarely visible in February. It is already decided. That is the biological reality most beekeepers miss. The outcome of spring expansion is not determined in spring. It is determined months earlier, in the structure of the winter cluster, in the age of the bees that survive it, and in whether a narrow physiological transition happens at exactly the right moment. Have you experienced this in your own hives? 2 colonies side by side, one thriving, one struggling, and no obvious explanation for the gap. If you have, this episode is built around that exact question. And if you find value in biology-based breakdowns like this one, a like helps this channel reach other serious beekeepers. The misunderstanding most beekeepers carry into spring is that colony growth is a response to warmth, that once temperatures rise, the colony simply expands. But that framing places the cause in the wrong location entirely. Warmth is a condition, it is not the engine. The engine is a specific type of bee, and whether enough of them survive long enough to make the transition possible. Historical beekeeping literature from the late 19th and early 20th centuries, from writers like Frank Benton, C.C. Miller, and the contributors to early volumes of the American Bee Journal, consistently return to one observation. The colonies that built fastest in spring were not necessarily the largest going into winter. They were the colonies that came out of winter with the right kind of bee. What that meant in biological terms took decades to fully understand. Here is the mechanism at the center of this episode. A honeybee colony does not contain one uniform population. It contains at any given time bees in radically different physiological states. The bees that carry a colony through winter, the bees that cluster through cold months, consume stored honey, and maintain heat, are not the same kind of bee that forages during summer flow. They are physically different, they live differently, they function differently. Winter bees, sometimes called diutinous bees, are characterized by elevated levels of a protein called vitellogenin. This protein accumulates in the fat body, a diffuse tissue distributed through the abdomen, and it serves multiple functions simultaneously. It supports immune resilience, it buffers nutritional reserves, and critically, it extends lifespan. A summer forager may live 4 to 6 weeks. A winter bee, carrying sufficient vitellogenin, may live 5 to 7 months. The colony's survival through winter depends almost entirely on whether it entered cold weather with a sufficient population of these physiologically prepared bees, not simply large numbers, the right kind. Here is where the spring expansion question begins to sharpen. When late winter conditions trigger the queen to resume laying, typically in response to lengthening day cycles and the first available pollen, the colony begins a transition. Winter bees must shift from a long-lived survival physiology to a shorter-lived active physiology. They must become nurse bees, feeding larvae, before they can become foragers. And they must sustain that nurse bee function long enough for the next generation to emerge, grow, and take over. This transition window is narrow, and it is fragile. If the colony enters it with too few winter bees, the emerging brood demand overwhelms the available nurse population. Larvae are underfed. Emergence is weak. The colony begins to contract precisely when it should be expanding. The cluster shrinks. The queen may slow or stop laying. By the time warm weather arrives in earnest, the colony is weeks behind, sometimes unrecoverable for that season's flow. Strong colony, weak surplus. This is not a failure of spring management. This is the result of a cascade that began the previous August or September. If you value biology-based beekeeping, consider subscribing. What most beekeepers misunderstand is this. The spring buildup is not a single event. It is a relay. The winter bees must hold long enough for the first spring bees to emerge. Those spring bees must establish nurse function before the winter bees expire. The first forager cohort must reach the field before the nectar flow peaks. Each handoff must succeed. A failure at any point in the relay breaks the chain. This is why 2 colonies in the same yard, same forage, same microclimate, same management, can diverge so dramatically by May. One relay ran cleanly, one did not. Historical beekeepers describe this divergence without always understanding its mechanism. They knew to check for what they called spring strength. They knew that colonies needed to be populous going into winter. They developed various rules of thumb covering at least 8 frames of bees at the end of season, ensuring visible pollen stores by October, reducing entrance size to preserve cluster heat. These were practical responses to a biological pattern they observed consistently but could not fully explain. The biology was real. The practices were sound. The mechanism just wasn't named yet. Let's examine the conditions that support a successful relay and the specific points where it tends to fail. The first variable is cluster size at the end of winter. A colony that reaches late February, covering fewer than 5 deep frames of bees, is working with a thin margin. Nurse bee demand from even modest early brood can outpace the available workforce. This is not a hard cutoff. Some small colonies do pull through, but the statistical risk increases sharply below that threshold. 5 to 8 frames of winter bees represents a more stable foundation for early brood rearing. The second variable is pollen availability. Vitalogenin levels in winter bees begin to decline when brood rearing resumes because the protein is redirected toward brood food production. To sustain the nurse function and begin building the next generation's fat bodies, incoming pollen must be available. In regions where early pollen sources, red maple, willow, alder, hazel, bloom reliably before mid-March, colonies have a natural buffer. In regions where pollen arrives later or where late cold snaps kill early blooms, colonies can enter a nutritional gap during the most sensitive part of the transition. This is a timing risk that requires active attention. A colony attempting to expand brood in February or early March without pollen income is drawing down reserves that may not be replaceable quickly enough. The third variable, and perhaps the least visible, is the age structure of the surviving winter cluster. Colonies that went into winter with a strong late summer brood cycle produced a robust cohort of young winter bees in September and October. Those bees are now 6 or 7 months old as February turns to March. They are near the physiological end of their viable lifespan. The colony's early brood, laid by a queen resuming activity in late January or February, will not emerge until late February or early March at the earliest. That emergence must happen before too large a fraction of the winter bees are lost. This is the relay's tightest handoff. The gap between the winter bees failing and the spring bees emerging is measured in days to weeks. A colony whose winter bees die faster than typical due to heavy varroa loads from the previous autumn or nutritional stress or disease may not bridge that gap successfully. Timing over products. That principle holds nowhere more clearly than here. What does this look like in practical inspection terms? A colony inspected in late February or early March that is expanding normally will show a central brood patch, typically 3 to 5 frames of capped brood surrounded by an arc of open cells containing eggs and young larvae. The cluster will be covering brood actively. Nurse bees will be present in numbers. The population may appear modest, but the density over the brood frames should feel intentional, tight, working. A colony in early trouble will show a smaller, more irregular brood pattern. The queen may be present and laying, but the patch will be fragmented. Small, scattered cells, inconsistent capping, gaps where larvae were laid but not fed consistently. This is not always a failing queen. It is often a nurse bee population that has thinned faster than the brood calendar can compensate. The intervention available at this stage is limited but not zero. Reducing the hive volume to match the actual cluster size, removing drawn comb. The colony cannot cover and keep warm, helps the existing population concentrate its thermal energy and nurse bee attention. A single deep hive body is appropriate for a small overwintered cluster. Empty space does not assist recovery, it divides effort. If a reliable pollen source is not yet available, and stored pollen is visibly low, pollen supplement patties placed directly on the top bars above the cluster, not in an upper box, not at the entrance, can provide nutritional support during the transition. Historical beekeepers used fermented pollen and pollen substitute mixtures with varying success. The principle is consistent. Protein support during early brood rearing reduces the physiological strain on the winter bee population. Now consider the colony that does expand cleanly. It entered winter with 6 or 7 frames of bees, not massive but solid. It went into cluster with a queen who had completed a strong late summer brood cycle in August, producing a robust winter bee cohort. It had visible pollen stored in the outer frames of its brood nest. Varroa levels were managed before that August brood cycle began, preserving the vitalogenin reserves of the developing winter bees. Mite-damaged winter bees carry reduced fat body stores and shorten faster. That distinction is not minor. It determines whether the relay holds. This colony begins early brood rearing in late January. The cluster does not break apart. It expands gradually outward from the center as temperatures allow. By mid-February, there is capped brood. By early March, emergence has begun. The new bees are summer physiology bees, but they are young with full fat body development, and they immediately enter nurse bee duty. The winter bees begin to die. but the transfer has already started. The cluster sustains its nurse function without interruption. By April, this colony may be covering 12 frames. By early May, before a strong nectar flow, it may be preparing to swarm. The beekeeper who does not recognize that swarm pressure as a sign of success risks losing the surplus to a caste swarm rather than a honey super. More bees, less honey, if the expansion is not managed. This is the fourth variable that receives too little attention in the spring build-up discussion. The relationship between colony population growth and the decision window for swarm prevention. A colony that completes the spring relay successfully will, under most conditions, begin swarm preparation at some point between late April and early June in temperate North American climates. This is not a management failure. It is the biological outcome of successful expansion. The colony is doing exactly what its biology directs it to do. The question is whether the beekeeper is present and prepared during that window, which historically has been described as narrow and unforgiving. A queen cell that reaches the capped stage is approximately 8 days from emergence. Once emerged, the prime swarm typically departs within 24 to 48 hours of first capping, before the cell caps in many cases. The decision window for intervention is measured in days. Historical management accounts from the early 20th century, particularly from apiaries, focused on comb honey production, where large populations were necessary and swarm control was economically critical, developed a range of techniques precisely because this window was understood to be narrow. The demery method, various forms of splitting, the use of drawn comb to give expanding populations space to move into, these were not arbitrary inventions. They were responses to a biological compression of timing that beekeepers observed season after season. There is a practical sequence that emerges from this biological understanding. The first task is assessment in late winter, not intervention. Assessment. A hive inspection in late February or early March should answer 3 questions. Is the queen present and laying? Is the brood pattern consistent with a functional nurse bee population? Is pollen either stored or incoming? If all 3 answers are yes, the colony is in the relay, and the beekeeper's role is to avoid disrupting it. Unnecessary manipulation of a small early spring cluster, pulling frames, rearranging brood, adding unnecessary space, can drop the internal temperature of the brood nest and set the relay back by days. Cold brood does not die instantly, but chilling events slow larval development, affect adult bee quality, and add stress to a population already operating on thin margins. The temperature the colony maintains within the brood nest, approximately 93 to 95 degrees Fahrenheit, is not passive. It is actively produced and defended by the cluster. The beekeeper who opens a hive for 20 minutes on a 40-degree day in March is not assessing, they are imposing a thermal cost. That does not mean early inspections are without value. It means they should be brief, purposeful, and timed to warmer parts of the day, when temperatures are above 50 degrees Fahrenheit and rising. The second task is a mid-spring population check, approximately 6 to 8 weeks after the first visible brood. This is the inspection that tells the beekeeper whether the relay succeeded. A colony that has bridged the transition will be growing visibly. Brood frames should now occupy the majority of one deep box. The population should feel crowded on the brood nest. Incoming pollen should be visible at the entrance on any warm afternoon. If a second deep box is not yet on this colony, it should be added now with drawn comb, if available, with foundation if not. A colony reaching this point without adequate vertical space will begin swarm preparation regardless of management intention. The timing of this expansion is not negotiable by the beekeeper. It is set by the biology. The beekeeper's role is to be ready for it. The third task is swarm management, and it requires the beekeeper to resist the instinct to delay. The classic mistake is waiting until swarm cells are already capped before responding. By that point, the prime swarm may be preparing to leave. The intervention must happen earlier, at the point when the colony shows population pressure but before queen cell construction has advanced. This is visible as congestion in the brood nest, bees bearding on the outside of the hive in cool weather when they have no thermal reason to do so, and the presence of play cups along the bottom bars of brood frames. A split made at this stage, removing the queen and several frames of brood and bees to a new box, redirects the colony's population impulse without losing the prime swarm. The parent colony raises a new queen. The split establishes a new colony. Neither unit swarms immediately because neither unit has a mated queen and a mature population simultaneously. The biological pressure has been redirected rather than suppressed. This technique requires drawn comb, adequate stores on the split frames, and a yard position that allows for wagers to return to one of the two units. It is not complicated, it requires timing. The colonies that fail to build in spring are not, in most cases, victims of bad spring weather. They are colonies whose relay was already compromised before winter set in. High mite loads in late summer, insufficient late-season brood cycles, inadequate pollen stores entering cluster, and small or uneven cluster populations going into cold months. These are the inputs that determine spring outcome. The beekeepers in the early 20th century who kept detailed apiary records noted this pattern consistently. The same colonies that came out of winter strongly were the ones that had been managed carefully in August and September. The spring was simply when the result became visible. Preparation determines outcome. The season's work happens before the season appears. Spring is not the beginning of the colony's year. It is the conclusion of the previous year's work. The bees moving from cluster to brood nest to foraging force are completing a relay that was set in motion months earlier in the late summer brood cycle, in the mite load management, in the protein stores carried into winter. What is visible in April is the outcome of decisions made in August. Understanding that sequence does not eliminate variables. Weather is real. Disease pressure is real. Some colonies fail despite careful preparation, and some survive despite apparent neglect. Biology is not perfectly predictable, but the colonies that build most reliably are the ones whose beekeepers understand the relay and prepare for it in the right season. If this breakdown was useful, leave a comment with your experience. Subscribe for more historically grounded beekeeping insights.